for four presentations for Hercules and one for HEATERNAL. At the end of the presentations, we have also scheduled for a short Q&A session, but I would like to tell you that if you have questions during the presentations, please throw them in the chat so that from a practical point of view, we will have the opportunity to address all or at least most of them without any delays because time is limited. And together with your question, please also share the name of your organization and, if possible, your short affiliation yourself. Okay. So enough with the instructions and the procedural stuff. Let's now start. The first presentation of the event will be given by the Hercules Project Coordinator, Dr. Abhishek Singh. Abhishek is an assistant professor in thermal engineering in the Department of Thermal and Fluid Engineering of the University of Twente. And his presentation will be an overview of the Hercules project. Okay, so Abhishek, the floor is yours. I will now mute myself and you can take it from here.
Thanks, George. My screen? Perfect.
Yes, we can see.
Good afternoon, everyone. As introduced by George, my name is Abhishek Singh from University of Twente, and I'm actually coordinating this project, HERCULES, which is about development of a high-temperature thermochemical heat storage solution for industrial heating applications. The heat source is renewable electricity. That's the primary source. A few details about the project. It started 2 years ago, and we are at the midpoint of our project. It's a 4-year project funded by European Union, Horizon Europe program. We have 10 partners across Europe. We have 3 national labs, DLR, CERTH, and RISE. Of course, University of Twente is also partner, coordinator. Then we have 6 commercial partners that covers the whole spectrum of expertise and knowledge that we need from the commercial side. So we have a technology developer, we have material scale-up company, and also end users that can direct us if the solution is in right direction or not. So as I said, the objective is to develop a high temperature thermochemical heat storage solution, but in a hybrid mode. That means you store heat sensibly and also chemically. This system will be developed and tested at CERTH, and that's the, let's say, end goal of this project. Now, from the chemical reaction side, we are using metal oxides as the reactive material. You can see here the reaction. So it's very straightforward. You have metal oxide, you provide heat, and you, in this, because of this heat, you at some point you release oxygen, and you reduce high valence metal oxide to a lower valence metal oxide, which still stays in the solid form. Oxygen is a gas, you take it out. You can reverse the process, and by doing so, you can recover the heat you stored in. It's the delta H, the enthalpy change of your reaction. But since you're also heating up the material, so you're also inherently storing heat in the sensible form, which also you could recover. And that's why these kind of reaction systems have much higher energy density than the sensible only system. But of course, it brings a lot of complexities too. In this project, we are focusing on using resistive heating as the primary heat source, hoping that it will be powered by mainly the renewable electricity. But we also intend to use industrial waste heat as, let's say, partial source of heating. It depends on the application, the level of temperature and amount of heat, waste heat available. But we will investigate that also in this particular project. And idea is to develop a flexible and sustainable solution which is cost effective and can actually provide heat for industrial applications. Here is a very, very simple schematic. Reality is, of course, more complex. But here you can see the heat source is actually renewable electricity, and you store heat in the storage system, which when you discharge, you provide hot air, which is more than 1000 degrees Celsius. And then this air can be used for industrial purposes. Now, there are some industries that require that level of temperature even hot air is needed. One such industry is steel making process. In that process, they require high temperature hot air as an input. So this system fits very well there also. And that's why steel is one of the application we are looking forward in this project. Besides this, we also have recycling that they also need high temperature heat input. So this kind of storage could be useful for them as well. And one of the main point here is the material we are working with or developing with is in the form of honeycomb or foam. So that's the key part here. What we expect development at different scales, material, reactor, and the system. Material, of course, is the key here. You could see some of the numbers, KPIs that we are trying to achieve. In fact, in some cases, we have already achieved those KPIs like energy density and also the production cost. So we are very much focused on exploring only those materials which are cheap, non-critical, and does not have any harmful effect on health or environment. Then we are, as I said, the final goal is to develop this particular storage reactor. So we are in the process of doing that, and we have certain expected KPIs for that we are trying to achieve. And from the system analysis, we have already started doing modeling for system scale understanding of the process, how you integrate Hercules with a particular application. And we already have partners looking for LC analysis and the trying to also assess the economic realities of such a system. Current status, we have developed successfully at certain scale the material that we would like to further develop and scale up. We achieved, let's say, much higher energy density than we expected, or let's say the target was. You will hear more about this in the next presentation. Then we have a pre-prototype under testing at CERTH. We decided to first have a small system tested, learn from it, and then go for a bigger prototype scale system. So that's in process. And we already have modeling efforts for system scale modeling, LCA, and the techno-economic analysis. We have first few results. Some of them we will share also today, and rest maybe for the next webinar. So at this point I stop. I think we are short on time. Thank you for listening. And I think we can move to the next presentation.
Thank you, Abhishek. Thank you also for the concise presentation. Let's say, I think it was right to the point as an introductory one, so thanks a lot, also respecting the time. Yeah, now we can continue with the second presentation. It's going to be on materials development and their shaping into structured bodies. The presentation will be given by Dr. Christos Agrafiotis. Christos is a long-time collaborator and he's currently a senior scientist at the Institute of Future Fuels of the German Aerospace Center, DLR. So Christos, the floor is yours. We can hear your screen.
Yes, I shared the screen, but I forgot to unmute myself. Okay, just a moment again. So here, I hope you can see it now, right?
Yes, we can.
Okay, so without losing any more time, I will present the relevant work here on the materials and the shaping, which is, let's say, mainly assumed by the partners DLR, CERTH, and LANDSON in this specific work package. So let me first of all tell you the idea of how this, let's say, project was set forth. So from industrial heat recovery, industry uses, let's say, the so-called regenerative storage systems, otherwise called copper stoves, usually with blast furnaces in order to recover industrial heat. This is nothing more than a fire brick pattern, okay, as you can see in the picture, in huge towers, wherein, let's say, the hot combustion gases from the furnaces are diverted. During normal operation, they heat sensibly these bricks, they charge, as we say, this brickwork, and when, let's say, we need some hot air, we can pass, let's say, colder air through these already hot bricks, get the heat out of them, discharge the bricks, and then drive this hot air back where it's needed in other processes on the factory, like drying or mixing with inlet air and so on. preheating it. So the similar principle is applied also in our, let's say, field where we're dealing with concentrated solar power. Essentially, we produce heat to produce electricity, and essentially the idea is the same, that concentrated solar energy is diverted to a storage module made out of porous honeycombs, whereas, let's say, under normal operation, we produce electricity. And this storage is essentially the same sensible heating storage as I described before to generate electricity when the sun is not available. So one can pump, let's say, heat to the steam turbine from the storage module. As the time went by, this whole system can be, let's say, autonomous from the heat source. One can use the same principle of storage through this kind of porous structures by, as Abhishek explained, by heating the air, not by solar energy or not from combustion gases, but from renewable electricity that it's abundant during the day from wind or PV, and otherwise it had to be curtailed. So in order not to throw away this electricity, one can think of one solution is to heat air and through this hot air to heat the bricks, and then do the same thing as we said before, to store this electricity first to heat and then again to power, to produce power of sun or when the price is high. So that's exactly what I said before. This kind of modules now, many companies advertise them as green heat modules, okay? And there are several companies in the business where essentially they advertise and they market cascades of these sensible bricks that can be operated with excess renewable electricity that otherwise had to be curtailed. The philosophy is similar. Honeycombs or bricks or brickwork, it's essentially pores flow through ceramics that are heated sensibly to high temperatures. And as you can see also, even in industrial, this concept in research, there are several studies. I chose one representative from MIT that exactly promoting the same concept, let's say resistively heating here directly the bricks, let's say, made of aluminum or silicon carbide with excess electricity, exactly to have round-trip electricity storage. Nowadays, there are much more studies on the same topic. Okay, what we can do, of course, we cannot outcost bricks, rocks, sand, and slag, which have been, let's say, also examined as alternative solid storage sensible heat media, but we can generate extra heat in the same volume during, let's say, normal process operation and exploit it together with sensible one, and essentially is to hybridize sensible with thermochemical heat storage. That's our approach, okay? So essentially we pass from the so-called plain bricks to what I like to call breathing bricks, which are essentially redox oxides made or coated non-moving flow through porous ceramics, and the future is that they can release oxygen upon heating, remain in the solid phase, and then inhale back this oxygen if, for instance, air is passed upon them to again generate heat through the reversible exothermic oxidation reaction. Okay, and how can we increase the storage density? As I said before, we have to make, let's say, this kind of oxides and exploit this kind of reactions as they are shown here, in a very generic scheme. Upon heating, the oxide is heated, it loses some of its oxygen, transforms to the reduced state of the oxide, and then when we need extra heat, we can pass, for instance, air through the body, the porous body, and then recover back the enthalpy of the exothermic oxidation reaction. The idea is, of course, we would like to have low-cost, non-toxic redox materials and high reaction enthalpy, but of course we cannot have all of this. The materials that already have been chosen and tested for this kind of applications span this range that you see there. With green are, let's say, the desired properties that each material has, with cost, the adverse ones. You can see, for instance, that cobalt oxide has extremely good cyclability and high reaction enthalpy, but it's of high cost and potentially toxic. Manganese iron mixed oxides, they are also non-toxic and cheaper, but they have lower reaction enthalpy. Other concepts, mixed magnesium manganese oxides, they have high reaction enthalpy and cyclability, but they need a very high reduction temperature to initiate, let's say, the thermal only reduction that it's mentioned as the first step above. And perovskites, which we will, let's say, elaborate upon, they have cyclability, low cost, they're non-toxic, and they can operate in a broad temperature range, but the reaction enthalpy is not as high as the previous one. Here is our first studies when we employed cobalt oxide, and so far, this, to the best of our knowledge, represents the biggest ever, let's say, proof of concept of this scheme, where we employed, let's say, about 90 kilos of cobalt oxide, which is black. It's coated on cordierite honeycombs, as you can see there, and in these two big units. And what I want to insist upon is, if you follow the thermocouple traces here during operation, what essentially we do is that we heat the material sensibly. When we reach this equilibrium temperature of this reaction at about 890 degrees, you see a constant plateau of temperature, which corresponds to this exactly, this temperature, to the reduction of all the cobalt oxide there. We keep on heating, and then we reach, let's say, a desired temperature, and then when we need the extra heat upon cooling, the material follows exactly the reversible process. At exactly the same temperature, you can see how it can provide, let's say, air of constant temperature at exactly the equilibrium temperature for an equal dimension of time, equal duration of time, which shows beyond any doubt the principle of how this hybrid, let's say, sensible thermochemical storage should work. So what's the problem? The problem is, as we said before, that cobalt oxide is expensive, critical, and potentially harmful. And furthermore, it expands irreversibly upon, let's say, prolonged cyclic. Here you see, for instance, a honeycomb made of cobalt oxide by our partners at CERTH, which after 27 cycles, you can see that the structure collapses because the expansion is irreversible, and eventually the whole structure is useless. Here you see it in a dilatometry experiment. The red line is the cycling between 300 and 1100, and the blue one here is the residual length. You see that the material is heated thermally and thermochemically, but then upon cooling, it does not return to its original dimension, but it's essentially longer, right? And this augmentation of the length is continuing until you have this effect that you see there. So we have found non-critical earth-abundant elements based on calcium, manganese, and iron oxides, that they are the blue elements in this so-called Herfindahl-Hirschman index, which demonstrates visually that any large-scale, let's say, high-volume energy application requires these abundant blue elements. Our materials, calcium, manganese, iron oxides, are definitely within the blue spectrum. And the idea, as we said before, it's the disadvantage is that they possess a lower enthalpy of oxidation, since they operate as a partial reduction mechanism rather than a phase change as the cobalt oxide. The idea is now, as we said, not only to find the material, but shape it to a suitable heat exchanger, reactor heat exchanger, that will be, let's say, operating. And here we get input from the automotive industry. We see exactly that these honeycombs here, used excessively in every automotive exhaust after treatment car, they present a very low pressure drop and a very high specific surface area for gas-solid reaction when compared, let's say, to solid particles or other packed media for packed beds. So we go in for high throughput flow-through porous structures like honeycombs and foams, which have these significant advantages, especially very low pressure drop. And also they are amenable to modularity, means that one can build a unit from several small pieces of the same, let's say, base unit, and also fine-tune this unit in a cascaded way along the length by using different redox materials along the length of the bed, and also sensible only materials in high or lower temperatures when these oxides do not operate. Also to vary the porosity along and across the bed by artificial porosity, let's say, along the periphery, and denser structures in the middle to level off the velocity of the air coming in, and also to combine different temperatures like different porous structures like honeycombs, foams, or 3D printed structures along this cascade. So one is very, let's say, has many degrees of freedom to play, not only with composition of the redox material itself, but also the structure, the porosity, and so on. And here, our colleagues at CERTH have started to make this kind of porous structures based on this perovskite composition. You will see some typical ones here, which are of the order of 1 inch diameter. You see how these are made with these extrusion dies, several variations with the cells. CPSI stands from cells per square inch, how denser or less dense is the structure. And here, for instance, we can see the finalized product that can be tested, and my colleagues at CERTH will present the testing results in the next presentation. So they can produce flawless sintered bodies of the desired compositions that can be very well characterized, and they are very robust to be tested later on. Ourselves, we also do porous foams. We cover, let's say, with a slurry polyurethane templates, and then we sinter the template, and we can come up with structures like this, which are, let's say, have porosity in 3 dimensions. They are not, let's say, one-dimensional channels like the honeycombs, and these structures in theory enhances radial mixing and radial heat transfer. Okay, and you can see here the variety of the shapes that we can make with holes here and there to fine-tune the porosity along the periphery or to be fitted to different reactors with thermocouples and so on. A larger scale extrusion was undertaken by our partner LANDSON Ceramics, where you see here specimens of 80 millimeters diameter, how they come out, again, practically flawless from the extruder. And here you can see a very nice, let's say, cross-section of the square channels that one can produce with this kind of technique. And also the variation can go on. One can, let's say, shape square modules to place them one in another, or hexagonal modules, as you see there, that will be presented in the next presentation by CERTH. So the last slide to conclude is that the idea is to integrate, let's say, thermochemical storage within sensible heat in the same way that is performed currently with porous flow-through ceramics to produce more energy and store more energy per unit volume. Of course, the advantages of non-moving solids only can circulate gases, nothing solid moves, and no mechanical parts at high temperatures. Also, these materials can be operated under air both during reduction and oxidation, so we don't need vacuum. As we said, they are abundant, inexpensive, and non-hazardous, and can use reliable recycled materials as well. There is a minimal pressure drop build up due to the use of extremely porous ceramic structures. And as I said, to the best of our knowledge, is the first time that such a systematic production of perovskite-made structures, ceramics, has been, let's say, reported in the open literature. Thank you very much. I hope I didn't get too much beyond the time limit.
Thank you, Christos. It took you a bit longer, but I think it was worth it, for sure. So thanks a lot for the detailed presentation and for sharing with us this information regarding the material shaping. Let me remind you to feel free to post your questions in the chat, if any, and together with your questions, please share the name of your organization and your affiliation. So now we are ready to move to the next presentation. This will be given by my colleague, Leonidas Chasapidis. Leonidas is a mechanical engineer and the project manager of the HERCULES project on behalf of CERTH. So he will give us an overview of the reactor, the HERCULES reactor, and the associated experimental testing of structures previously presented by Christos. Leonidas, the floor is yours.
Thank you. Good day, everyone, and welcome also from us here at CERTH to the first HERCULES online workshop. I'm Leonidas Chasapidis, and I will be presenting this work on behalf of CERTH team, George Karagiannakis, Chrys Apagoura, Nikos Vlachos, and Kyriakos Fotiadis. Today I will talk about the testing activities we perform here in CERTH for the HERCULES project. Okay, our primary objective is to quantify how much energy can be stored using both sensible and chemical means, particularly through redox reactions. We are also focused on confirming that the stored energy can be effectively transferred to a working fluid such as air. Another goal is to validate the thermal and chemical stability of these materials and final structures under cyclic conditions, specifically over 200 cycles at temperatures exceeding 1000 degrees Celsius. And finally, we aim to achieve an energy density of greater than 200 kilowatt hours per cubic meter in the 300 to 1100 degrees Celsius range. In the lab, we test small structures around 1 inch in size under realistic conditions. These samples are heated in a conventional furnace and exposed to airflow pressures between 1 to 5 bar and temperatures ranging from 600 to 1100 degrees Celsius. We monitor the temperature at 3 points: the flow inlet, the substrate, and the flow outlet. The redox cycles may be isothermal or dynamic, depending on the test. This setup help us evaluate material behavior and performance under conditions that simulate real-world industrial heat systems. During redox cycling, we observe that the airflow temperature drops during reduction and rises again during oxidation. While the inlet temperature remains stable, the substrate and outlet temperatures fluctuate due to the chemical reactions. These variations help us compute the energy exchange with the substrate and the energy delivered to the airflow. This data is essential to quantify the effective energy storage and release during cycling. This diagram down there also shows here highlights our thermocouple placements. We measure the inlet temperature, the internal or substrate temperature here, and the outlet flow temperature. These points are critical to capturing how the heat moves through the material and the system during the redox cycling. So this slide presents two typical experimental procedures: dynamic redox under airflow and isothermal oxidation at various temperatures. The graph shows corresponds to an experiment conducted at 900 degrees Celsius under nitrogen flow. We observe 4 consecutive test cycles, each ramming the temperature up to 1100 degrees, where the reduction phase occurs. The blue line represents the oxygen concentration, which rises above the atmospheric levels during these cycles. In the dynamic redox process, oxidation begins immediately after the temperature starts to decrease after the peak. In contrast, during the isothermal oxidation, the system is cooled under nitrogen flow to the target temperature, which airflow is introduced to trigger oxidation. As shown, oxidation leads to a rapid increase in the substrate temperature and the downstream here and the downstream gas temperature due to exothermic reactions. The upstream temperature, you cannot really see it here, but remains unchanged as it is unaffected by the reaction zone. These experiments help us compare the performance of different materials, structures, and geometries. So let's now look at some indicative results. The bulk density of the sample varies from 0.81 to 2.25 kilograms per liter, depending on the structure and geometry. Specific heat capacity ranges from 1.1 to 1.5 joule per gram Kelvin, and the thermal conductivity between 1 to 2 watts per meter Kelvin. The non-stoichiometric parameter delta reaches up to 0.12, depending on material composition. And the total energy can reach up to 818 kilowatt hour per cubic meter across the range of 300 to 1100 degrees Celsius. Of this, about 1/4 to 1/3 comes from the chemical storage contribution. This shows that the integrating redox active materials can significantly enhance total energy storage compared to traditional sensible heat methods. So we are now moving on beyond lab scale work. The pilot system is designed to scale up the testing of these redox structures and validate their performance in larger setups. These include energy density, but also long-term operational stability under cyclic use. We aim to bridge the gap between small-scale experiments and real industrial applications. So this slide can give you a visual representation of our pilot system under construction now. It is an essential step towards demonstrating that our material and methods can be practically implemented at a meaningful scale. So to summarize, redox active porous structures offer a promising route to high temperature energy storage. The thermochemical contribution can increase total energy density by over 40%, with lab scale tests exceeding 200 kilowatt hours per cubic meter. We are now validating this at pilot scale, focusing on long-term durability and system performance. Our next steps will include comparing pilot results with lab data to assess scalability and commercial potential. So thank you very much for your attention.
Okay, good. Thank you, Leonidas. Thank you so much. In the meantime, there have been some activity in the chat of the Zoom. For those of you that you have not checked it yet, you can find there a link to our YouTube channel that shows the main, in fast forward, of course, the main step for the construction of the reactor, the pilot reactor that Leonidas described in the last slides. The answer to the next question, if the recording file will be provided to the participants, the answer is yes. And yeah, that's it for now. So let me ask you again to throw any questions there together with your affiliation. And now I think we are ready to move to the last presentation regarding HERCULES project, which will be on system modeling and simulation activities. This will be given by Granto Natama Putra, who is a master student at the University of Twente, who works together with Abhishek in the coordinating team. So Granto, if you are ready, we are all ears.
Okay, thank you. Can you see my screen?
Yes, but not in presentation mode, I think. Now you are on presenter.
Okay.
Good.
Okay, thank you. Okay, so now I will be presenting my research about the system level simulation of an integration of thermochemical heat storage system with renewable energy generators and also heat intensive industry. And in this case, I'll be using steel manufacturing case. And the structure of this presentation will be introduction, integration concepts and scenarios that I use, the physical modeling, model validation, and the system dynamic response. And the objective here is to find which configuration is technically feasible and economically viable to integrate the renewable electricity generators, thermochemical heat storage, and existing heat-intensive industries. Because we know that the renewable sources like wind turbines or solar energy has a fluctuating supply, and it is also costly nowadays. And our storage properties, as has been explained before by other colleagues, that it has technical limits like the temperatures, the capacity, etc. And it is also costly nowadays. And on the other side, our industry requirements, they need constant temperature, constant high temperature, power, and also it has to be continuous, the heat supply. And for the case study here, this is a steel making process. Just briefly about how they do the steel making here. We have iron ore, limestone, and coal. The iron ore and limestone going into the sintering process, and then we have sinter. Then the coal is going into the coke oven, then we have coke. And these two materials is coming into the blast furnace, and there is hot air blast coming in from the bottom of the blast furnace. And this hot air blast is actually cold air that has been heated inside a hot blast stove. As Christos already explained before, hot blast stove, you can also say this as a copper stove. And because essentially inside the hot blast stove is just like brick, and this is just a sensible heat storage. After some time, the temperature of these bricks is going down, then we have to reheat these bricks. And how do we reheat that? We are burning blast furnace gas. This is a byproduct from the blast furnace with air, and this combustion gas will be heating up the brick inside the hot blast stove. And the temperature of this combustion gas is around 2000 degrees Celsius. And when the copper stove or the hot blast stove is heating up the air, that is the air going into the blast furnace, we are calling it on blast mode. And when the hot blast stove is under charge process, then we are calling it on gas mode. In this case study, the gas power supply to the hot blast stoves is 100 megawatt approximately, and it is equivalent to almost 70,000 tons of gas annually. So because the blast furnace requires constant or continuous supply of hot blast air, then there are sometimes 3 or sometimes also 4 hot blast stove coupled with 1 blast furnace. And as you can see here, this is the timetable or the sequence of the working of the hot blast stove. Let's say we are having 4, then when the first stove is going on blast, and then the other 2 is on gas, and then the last one is idle before it goes into the next step to the on gas process. So from this timetable, you can see that at any time there will be 2 stoves doing on gas mode. So jump into the integration concept here. I'm proposing the integration to be like this. So as you can see at the left side, we will I'm having 2 HERCULES modules that will be working alternately. So when the first one is doing discharging, which is the air is coming into the HERCULES and the preheated air is coming to the hot blast stove, the second module is going charging mode. And all of these are controlled using PLC modules in my model. And the renewable energy power generator here that I'm using is wind farm, because based on our calculation, we found out that wind energy has the lowest levelized cost of energy compared to solar farm in the Netherlands. So we are moving on with the wind farm, and the amount of air coming in to the hot blast stove is around 43 kilogram per second. And the Hercules model here, this is the simplified model that I use in my model, in my software. This is a cylindrical tube with a honeycomb inside, and at the outer side, this is the insulation and steel casing. And for this study, I'm using cobalt oxide with corderite composite as the kinetics properties of the material. And the delta enthalpy during reduction and oxidation is plus minus 196 kilojoule per mole. And here I'm assuming that we have an evenly distributed heating element inside the thermochemical materials. So whenever there is electricity power coming in, we are assuming the power is distributed evenly. And yeah, so the model also I'm using thermal resistant based transient model. And in this model, I'm considering all about the conduction, convection, and radiations heat transfer that are to mimic the reality of the implementation of this technology. And the model has been validated using experiment result from a paper from Teskari. And it shows that the maximum deviations is less than 3%. So it means the model is good enough, and I can use this model further to be integrated with the wind farm model and also the hot blast stove model. Then the system dynamic response here, as you can see on the right side, this is the amount of natural gas reduction versus the amount of number of turbines and Hercules module mass. As for your information, one turbine installed capacity is 4.2 megawatt. So if you have 10, then the maximum capacity is 42 megawatt. And I'm using the properties of Vestas V150 model in my software. And as you can see, as you have more turbines, you will reduce more gas. And this amount of gas reduction is linearly correlated with the turbine counts, but it is not related with the Hercules module mass. However, we have to optimize this configuration so that we know, okay, so how many turbines is the most optimum configuration. Then I also did benefit to cost ratio analysis, sensitivity analysis with two independent variables, number of turbines and module mass. And in here, as for the revenue, I considered monetized gas reduction plus carbon tax reduction as forecasted in 2040 per ton of CO2 is around 150 euro. And also I'm assuming here that the total maximum life cycle of the material is infinite. It means if we operate this for, let's say, 20 years, we don't have to change the material. And as you can see, the highest benefit to cost ratio is when the number of turbines is 18 and the module mass is 100 ton. And from here, we can see that the benefit to cost profile doesn't linearly correlate it with the amount of reduced gas. So increasing the amount of turbines will not always translate into a higher benefit economically. And by using this configuration, it is forecasted that we can reduce around almost 22,000 tons of gas reduction, which corresponding to 32% of the total current consumption. So the summary from this research is integration of Hercules with renewable energy generator and steelmaking plant or any heat-intensive industries is technically feasible and economically viable. And for these specific case studies, 18 turbines and 100 ton of Hercules module will yield the highest benefit with 32% reduction in total from the total gas consumption. And because of this integration, it gives the flexibility to the company to modify the blast furnace, because we are no longer use that high amount of blast furnace gas, right? So it opened the possibility to implement new technology like DRI process for steelmaking, so that maybe we can also use hydrogen. And also, the future outlook for this model is to modify to include new material, as Abhishek has said before, like CS10MO redox material, to know the dynamic response and also the techno-economic analysis. Thank you for your attention.
Thank you very much, Granto. I think this presentation was very useful in the sense that it provided, let's say, the general context and also gave us some potential application areas and some numbers. Indicative, of course. This is in progress for work. Thanks a lot. So now I think
Thank you.
are ready. We are ready to proceed with the last presentation of the event, which will be dedicated to the HEATERNAL project and will be given by Sylvie Dural, the coordinator of HEATERNAL project and also European projects manager at CEA Limited. So Sylvie, whenever you are ready, please share your screen.
So, good afternoon, everyone. I'm Sylvie Dural from CEA, a French Public Research Center. And so I'm the coordinator of HEATERNAL project. So today I'm pleased to introduce HEATERNAL project during this workshop, and I would like to thank for this invitation. So I would like to begin by saying a few words about the general context of this project. As you know, we have to face climate change and environmental impacts due to human activities. We have to face also geopolitical events and rising energy costs. So let me give some data. Industry in Europe released 351 million of tons of greenhouse gas during the year 2020, and the energy used for direct heating is mainly covered by natural gas, up to 50%. So it's very big. So consequently, the European Union has fixed some objectives to be achieved by the year 2030, such as reducing gas emission, and by 50% compared to the 90s, and increasing renewable energy up to 40%, and energy efficiency up to 13%. So in this difficult context, HEATERNAL develops a thermal energy storage to meet industrial needs of high temperature heat. Globally, this storage will be able to satisfy the need for decoupling the heat generation from the heat used in industrial processes. And this storage will be able to generate heat during off-peak times, and so provide some quite flexibility in energy demand. And specifically, through HEATERNAL project, we expect to develop a short-term thermal storage up to 48 hours. And we expect to develop some new materials for its storage dedicated to medium and high temperature process. And so by this way, we expect to enhance the awareness of the challenges and benefits of its storage in industry, of course. HEATERNAL, so it's a quite long acronym. It means Innovative High Temperature Thermal Storage for Industrial Applications. And this project is funded by the European Union under a program. It has begun in May 2023, and it will last 3.5 years. And this project aims at upgrading the HEATERNAL technology from level 2 to level 5, validating the concept, of course, through experimental tests in representative operational conditions. The project brings together 11 partners based in Europe, mainly in Spain, Portugal, France, and Belgium. And 4 partners are public research teams who are focused on prototyping, thermal modeling, phase change materials development, and 3D printing. And this project also involved 4 manufacturers, 2 from the ceramic sector and 2 from the metal industry, and also an equipment manufacturer, a society specialized in life cycle analysis and techno-economic analysis, and lastly, a society experienced in dissemination and communication. So,
sorry, Sylvie, your slides are not changing. I think it's.
Sorry, I forget the screen. Sorry.
Oh, no problem. Yeah, thank you.
Okay. Thanks for the remarks. We know that in many cases, industrial processes require continuous high temperature heat and release some millions of tons of carbon dioxide into the atmosphere. So unfortunately, no viable solution exists today for the decarbonization of these processes. Therefore, a short-term thermal energy storage will be an efficient solution since it will enable to replace fossil fuels by industrial waste, heat, or renewable electricity. So the aim of HEATERNAL project is to develop an innovative thermal energy storage operating at high temperature. So the HEATERNAL concept is based on an hybrid storage using ceramic and phase change materials, so-called PCM. And this hybrid unit is represented on the top picture of this slide. And the lower picture shows that the storage would be able, in fact, to operate in 3 temperature zones, depending on the industrial application, and in the temperature range from 600 to 900 degrees. So each PCM in each zone undergoes a phase change at different temperatures. And thanks to this transition phase, I would say, each PCM enabled to increase the energy density of the whole thermal storage. Thus, the total amount of the stored energy will be higher than for sensible storage, which is illustrated by the graph at the top right of the slide. Also, in HEATERNAL, we address 2 technologies of the refractory material. The traditional one is based on casted bricks, and a more prospective technology is based on additive manufacturing. So precisely, in HEATERNAL project, we had the objectives to develop some composite materials of ceramic PCM for thermal storage between 600 and 900 degrees with some requirements. Its storage capacity over 400 kilowatt per cubic meter, proven lifetime over 1,000 hours, and the materials with low energy and carbon footprint, free from CRM, not toxic and safe, and easy recycling. So taking into account all these requirements, the PCM we have developed during the project are pure aluminium or binary and ternary alloys from aluminium, copper, iron, silicon, manganese, and titanium system. So considering the integration of the HEATERNAL solution in industrial processes, we have studied 3 use cases. The first one concerns the aluminium industry, represented by Alcoa company. And in that case, renewable energy will be stored as high temperature heat during the production of this low cost and intermittent energy. Then the stored energy will power continuous operating calciner. And the second use case is the ceramic industry, represented by Torresi, the company. And for this case, in some industrial waste heat from a continuous process will be stored and reused in a batch process, such as a ceramic furnace. And the store heat will be used to preheat the air between 650 and 900 degrees. And the third use case is steel industry, represented by Ugitech. And for this case, industrial waste heat will be stored to heat a steel furnace during a natural gas shortage or cutoff. And this storage will also be used to maintain the furnace temperature during the weekend when the process is not running. So we see that in all these cases, internal storage will enable to reduce the use of natural gas. So I propose to have a look of the project implementation. As all the European project, this project is divided into some work packages, and 5 of them are technical packages. So I will describe very briefly. Work package 3 is devoted to materials development, and we have work package 4 devoted to the thermal mechanical design of the storage. Work package 5 is focusing about the building and the testing of the prototype, and work package 6 will study the scalability and the integration of HEATERNAL solution in industry, and work package 7 will deal with the techno-economic, environmental, and social issues, and also exploitation plan. So I would tell that in this project, we have several short-term objectives. The first objective is to build and test a 50 kWh prototype in order to validate the HEATERNAL concept, maximize the thermal performances of the storage unit, simulate the full integration of HEATERNAL thermal energy storage into industrial processes in order to ensure, of course, the rapid implementation, and thus encourage stakeholders to invest in some developments at a high level maturity. And lastly, we have to ensure the economic viability and environmental sustainability of this system. So, as a matter of course, the long-term objective of this project is to reduce the carbon emission from high-temperature industries by 40% by the year 2040, while reducing their dependence on fossil fuel, mainly natural gas. So this brings us to the end of general presentation. So I suggest you to visit our website, so HEATERNAL.eu. And now, and thank you for your attention, and that's it for HEATERNAL.
Okay, thank you very much, Sylvie. That was really useful and informative. In the meantime, okay, we have exceeded our official time by 3 minutes, but I think there is a question that we can answer in the chat. This is a question for you, Sylvie. It's by Nicholas. The question is, and that was actually a question from my side also, to tell you the truth. It seems that the PCM material that we develop actually goes to fully liquid phase, right? The container that must keep it, that must contain it, let's say, must keep it from pouring away. So solid, liquid, you need a container to prevent, let's say, leakage of the liquid from the container. Is this right?
Okay, so it's a good question about HEATERNAL technology. And so for the moment, we have developed a prototype with traditional bricks and aluminum as a PCM. So we have studied the compatibility between the traditional ceramic and the aluminum as liquid phase. And so we have observed there is no how to say, no pouring of the liquid towards the ceramic. We have a very good compatibility with the two phase, the solid ceramic and the liquid PCM.
How do you achieve that? Are you doing it via do you infiltrate, let's say, the alloy inside the ceramic structure?
No, in fact, we have done some tests in a small oven, and we have put in contact some ceramic sample with aluminium sample, and we have increased the temperature of this oven, and we have observed the behavior of the liquid on the surface of the bricks. And we can measure the angle, the angle of between the surface of the ceramic and the drop of liquid aluminium, and we can conclude there are no interaction between the two materials.
Okay.
Because we have a high angle, wettability angle is exactly terms.
Okay, understood. Thanks a lot, Sylvie. It's already 6 minutes past, so past our official ending time. So I can see no further questions in the chat. I would like to thank you all. It's Friday evening, so I don't want to keep you much. Okay, the weekend is coming, so thank you all again for joining us. I hope that you have found our event useful. Thank you, Sylvie, particularly yourself, for accepting our invitation and for participation of HEATERNAL project.
You are welcome.
Workshop that we organized. So thanks a lot. As I told you, there will be this was recorded and it will be posted in our YouTube channel. All participants will receive the link. Okay, and in the meantime, if you have further questions, please feel free to reach out to us. We will be more than happy to discuss with you and probably, why not, establish future collaborations. Thanks a lot. Thank you very much for being with us. And I'm wishing you, on behalf of Hercules and HEATERNAL Consortia, we wish you a very nice weekend. Thanks a lot. Bye.
Thanks, everybody, and bye-bye.
Thank you.